there is a busy and productive organization devoted to making history in its own special way. That organization is the high-speed track at Holloman Air Force Base. This is the track. A pair of welded crane rails spaced 7 feet apart, stretching nearly 7 miles along the basin floor. The left or master rail is aligned to within plus or minus 5/1000ths of an inch of a reference line. The right or east rail is aligned to the master rail to within plus or minus 1/100th of an inch. The direction of the track is almost due north.
During 1954, we were conducting a series of track tests on human responses to acceleration, deceleration, and wind blast, which gained a certain amount of recognition. The effects of that run were relatively negligible, but the data obtained was invaluable. The instrumentation consisted primarily of sensors mounted on my body and the sled, plus cameras to record various stages of the run. Braking was provided by the momentum exchange technique, still in use, I might add. Let's take a look at how this system operates. There are vertical slots cut at 11-foot intervals along the entire length of the track. Masonite dams are installed in the slots, and the trough is filled with water.
A large steel scoop on the sled cuts through the masonite barriers, picks up the water in the trough, rotates it 180 degrees, and pitches it forward. Reversing direction of 1 pound of water produces approximately 2 pounds of retarding force. This is momentum exchange. Depending on the specific project's braking requirements, the dam heights are computer determined. The masonite is then cut and positioned in the trough to within 1/32nd of an inch of the required height. This technique is used to stop dual rail sleds.
The other principal system of braking involves the use of plastic water sausages for monorail tests. These water-filled bags are placed on the rail at a predetermined location, and a braking force is applied as the sled impacts the bags.
In 1956, the Holloman test track was extended to 5,000 feet. Up to that time, the 3,500-foot track had been used for 6 years and recorded some 230 separate test runs. Slightly over 1 year and 117 test runs later, in August of 1957, the 35,000-foot track came into being. The scope and versatility of the present track, lengthened 500 feet in 1966, to permit specialized blast testing, really becomes quite difficult to describe, at least within the confines of this film.
One of the unique features of this track is 6,000 feet of rainmaking equipment. Such testing makes up a major part of the track's workload and is designed to study the effects of an artificial rain field on experimental and operational radomes, nose cones, and materials. The adjustable spray heads are spaced at 8-foot intervals and are able to generate a rain field of variable drop size and variable rain rate.
This rain-making equipment is only an example of the wide range of services offered to any agency interested in testing on the track. Instrumentation, of course, is really the key.
This is Midway, located at midpoint along the track. Housed within this two-story blockhouse is the mass of electronic equipment used to provide both customers and project people with the desired data on each test run conducted on the track. For example, Sled profile measurement station. Sled position versus time data is received here and recorded on magnetic tape and later computer converted to a velocity and acceleration information. The method of obtaining such information is unique. At 13-foot intervals along the track are light beam interrupters. During the test run, a sled-borne sensing head with a light source and a photosensitive pickup crosses the interrupter. The resultant break in the light beam produces a voltage pulse which is telemetered to Midway and recorded. The telemetry receiving and recording equipment and timing equipment at Midway are some of the most sophisticated now in use. In addition to the conventional frequency-modulated FM system in use, there is a capability for receiving and recording pulse code modulated PCM, pulse duration modulated PDM, and pulse amplitude modulated PAM telemetry. On the roof of Midway is the Track Safety Control Center. During all countdowns and runs, and until the all clear is passed, this center is manned by a senior controller and his assistants to ensure that all safeguards are enforced.
The second part of the tremendous instrumentation setup here at the track involves the use of optical systems. There are 73 of these camera stations located at 500-foot intervals along the track. Use of this system provides optical time-distance data for each run. In addition, surveillance cameras are set up at the camera pads and tracking camera towers. There are also sled-borne camera stations and portable units for optical data recording of specific events as the sled traverses the track. It is not uncommon for 50 or 60 cameras to be used on one test. Some of the cameras photograph the sled at a rate of 100,000 frames per second. This complex includes track headquarters, instrumentation and engineering laboratories, shops, offices for contractors involved in current test programs, and propulsion system storage and loading facilities. Both liquid and solid propellant rockets are being used for sled testing. There are advantages and disadvantages to both. A number of things dictate the type of propulsion system. Economy is always a factor. There are such variables as availability of specific propellants, the ease or difficulty of storage, sled size, acceleration rate, and thrust controllability. All must be considered when carrying out planning and execution of any program. In the area of the test vehicles themselves, there are over 100 available, ranging from tiny high-velocity monorails to massive dual-rail sleds. The size, shape, weight, and frontal area of the payload are extremely important in determining the type of sled for a given test. Computer runs are usually made to determine the best combination of propulsion system and test vehicle. Based on specific program requirements, the Track Directorate does design and build special sleds, if none are available in the inventory. The one area we haven't covered concerns the blockhouses at the track. There are 4 permanent blockhouses. There is one at the north and one at the south end, one halfway down the track, and one 3,000 feet from the south end. In addition, there is a portable fire control trailer. This arrangement permits total flexibility. Sleds can be fired at any location and in either direction.
Each blockhouse contains communications equipment, sled firing circuits, and telemetry pre-firing checkout equipment. As many as 100 channels of sled data are controlled and monitored from the blockhouse prior to firing. Enough of the physical layout here at the Holloman track. It is big and impressive installation staffed by skilled, dedicated professionals. All the planning, coordination, designing, and computation come into sharp focus as the sled sits on the end of the track before being fired. For the next few moments, while we wait for the launch, I want you to watch the drama of the track as it unfolds almost daily. The track to date has conducted over 4,500 test runs on projects covering missile guidance systems, aircraft ejection systems, rain erosion studies, impact studies, and biomedical explorations on both man and monkeys. This has made the Holloman track one of the foremost research and development facilities in the United States.